Good morning. Uh, Day 7 calculus. Let's get to it. We're going to be talking about piecewise functions. Now, if you are unaware, a piecewise function is any function whose domain is split into multiple functions. What that means realistically is that instead of having what we call a smooth function, or even what we call a continuous function, which we'll talk about later on in the summer, instead of having one of those two things, which you can imagine from the thought of what that's going to look like, you're going to have what's often a discontinuous function or a non-smooth function. Meaning that this is our functions where, because of how they are designed, they have fundamental places where the function breaks. In fact, let's take a look at an example of one of those using Desmos. This is an example of an incredibly diverse piecewise function. You can see how this function is broken into 4 pieces. There's the red piece, which is defined by this equation. And notice how this equation only applies to very specific values. The domain is not every number, it's only numbers that are less than -1. Here, this blue one is also defined as being only between values of -1 and +1. And it follows this functional rule instead. And so it's a function that's broken into pieces. This left piece has its own equation and rules. This middle piece has its own equation and its own rules for where the domain is. And there's even a third and fourth piece here. This one here in green is between 1 and 2. And notice it has its own equation, which is separate from all the other ones. And between anything bigger than 2, it follows this equation. And so you can see how this function follows very different rules. And how there's some things that you don't see in other functions. Like, you notice how there's a sharp point here at this value that's listed as undefined. Like, this sharp point is an indication that the function has made some massive shift. You don't see this in an exponential function. You don't see this in a polynomial. You don't see this in a log. You don't see this even really in trig functions. You just don't see stuff like this. You don't see hops where it suddenly jumps from being here at 2,3 to being up here at 2,4. Like, you don't see that. It doesn't happen. No other functions have these randomness to them. But as you might imagine, this is a fairly straightforward one, but many functions act this way. Many functions interact this way. They don't follow predictable paths for the entire length of the function, This left-hand side could have been true for everything less than -1. But after -1, maybe it does something different, In science, you see this happen a lot, where you have things like thermic reactions, where suddenly your volume was following one particular functional graph, and then because it hits a flash point, it follows a different function instead. This can happen. It happens in things like a radioactive ignition. So, like if you talk about setting off an atomic bomb, there hits points where it doesn't follow these nice smooth curves the entire time. There's chaos. There's breaks. There's places where the function has sudden and unpredictable shifts. And piecewise allow us to look at these functions and see them as what they are, pieces of a larger function. And so we can talk about all 4 of these graphs as one big function with 4 separate parts, or pieces as you might call them. That is why they're referred to as piecewise functions. They are piecewise because they're graphs that break down into pieces and follow rules that are specific to those pieces. Now, anytime we talk about piecewise functions, it should be noted that when you talk about piecewise functions, these are split domain functions. Meaning, your inputs are specifically applied to a specific function. I use specific too many times. Let's look at a classic piecewise function. So piecewise functions are often illustrated with the curly bracket And the curly bracket is split into two components. The components need to contain two pieces of information. It needs to contain a function, so I'm going to say like x squared minus 1. And it also needs to contain the domain you're looking at it for. Something like x is less than 3. And the other one could be something else. X is greater than or equal to 3. So what this means is the top function is the function you should apply if your number is less than 3. So for example, if I look at this function asked, okay, how would I evaluate? Remember, evaluate means to plug in. And so let's give a couple examples here. What if I ask about f of 0, f of 2, f of 3, and f of 4? Well, how do we evaluate these? Well, if I want to find out where f of 0 is, so that means the place where I would plug in 0 into this function. Now, you might be like, well, which one? Do I plug into both? And the answer is no. No. Because the number is a 0, 0 can only be applied to the top domain, because 0 is less than 3. 0 is not greater than or equal to 3, so the bottom one doesn't apply. The top one is how we will find our solution. 0 squared minus 1, which is, of course, negative 1. And that is the only solution, because at the point of 0, only the top formula is applied, because 0 is only in the top formula's domain. At 2, you can see that 2 would also apply the top one. It'd be 2 squared minus 1. 2 squared is 4, minus 1 would be 3. And so f of 0 would be negative 1, because we plug 0 into the top function, because it's in the top function's domain. F of 2 would be 3, because 2 is in the top function's domain, and so we plug 2 in and get a value of 3. But f of 3 is different. F of 3 is in the bottom function's domain. And so when we plug it in, we'd have the square root of 3 plus 6, which would be the square root of 9, which is 3. The fact that these are the same doesn't mean anything. This just means that f of 2 and f of 3 have the same value. That happens more often than you could possibly imagine. It's a coincidence. Ignore the fact that they're the same. This could have been any number. In fact, f of 4 is also only in the bottom one's domain, so we plug it in, square root of 4 plus 6, which would be the square root of 10, which is a decimal. And in fact, let's take a look at what that graph would look like. Okay. So in this case, we have the first function where an x is less than 3 is x squared minus 1. So notice that to the left of 3, every time we plug in a value, it represents that graph. Notice it looks like a parabola, because less than 3 fits the parabola's mold. It's x squared minus 1. But once we get to 3, there's a sudden shift. It starts following this blue path instead. It has a hard stop up here. And in fact, you'll notice that up here, 3 is undefined. Why? Well, for one very, very simple reason. 3 is not in this function's domain. And so I can't plug in 3. I can only plug in numbers that are less than 3. 3 doesn't fit that mold. So 3 is actually undefined. Notice that any number less than it is defined. You can get very close to it. If we zoomed in, we can get closer still. But as soon as you get to 3, this function no longer is applied. You have to use the other function instead. And this is why it's piecewise. The left-hand piece is only applied in this domain. Every number less than 3. The right-hand piece is only applied to every number bigger than 3. This makes it piecewise. Now, your first few homework assignment problems, you only have 4 of them. That's pretty short. But each of them ask you to do the same thing we're asked to do in this first problem we did together, which is to be able to evaluate. It's not as easy as it seems. We're going to do a couple of examples of this. The second piece asks you to talk about what's the domain. And the big thing with questions about the domain is usually, concerned with either the same things as before, where you have radicals, or where you have fractions, but also here. we could have the possibility of having a broken system. Sorry. Okay, just real quick before I go on. We can use the graph to talk about the domain in this one by asking the same basic components, all right? Is there a place where we stop having the ability to draw? Now, if you're using Desmos, this is how you type it in. Copy this format. So you would do y equals, you do the parentheses, or in this case they're curly brackets. They're on your keyboard next to the enter key. If you're doing it on your phone, you usually have to go into the ABC menu, and they're right here. Okay? And so to type these in, like for example, let's look at our next problem. Another piecewise function. Okay, let's look at the piecewise function. F of x equals 2x minus 1 when x is less than -2, and negative x plus 1 when x is greater than -2. Let's type this into Desmos together. So if you're using Desmos, let's go ahead and pull it up. Excuse me. Here we go. So I already have these typed in, so I'm going to not cheat here. Let's do it. So we would do y equals, go to the ABC menu, we open a bracket. Now, it doesn't matter necessarily which order you put it in. I like putting the function in first, but you can actually do the boundaries first. So I would do, in this case, x is less than -2. You then have to use a colon, which is the double dots. And then you define the function, which in this case was 2x minus 1. Close our brackets. Oops. Can we close our brackets? There we go. And so if we look at a graph, you can see down here is my function, and it's beautiful. I can do the same thing up here. I do the second function, which is y equals negative x plus 1. I'll need to zoom out a little bit. Oops. I need to go by boundaries. So we use the brackets. And I should be able to do it on the other side just the same. X is greater than -2. We didn't like it. Okay. So that's good to know. On Desmos, you have to put the boundary first. Otherwise, it will not like it. You have to put the boundary first, and then you put the function second, which is kind of the opposite of how a lot of your questions are written in your homework. So do note that if you're using Desmos. So in this case, there's my function, and there's the two pieces. I have the blue piece and the red piece. Red piece represents the first function. Notice its domain is everything less than -2. So if I want to go to -3, I'd have to go and plug it into the red function, because -3 is applied at the negative function's value, which is at -7. If I plug in -10, I'd have to go to the red function, because it's the one who's in the domain. If I want to use something like 4, well, that's in the blue function's domain. So I go over here to 4, and see that at 4 we have a value of -3, it looks like. There we go. Do note that even when graphing, you can see that there is a problem. Because up here at -2, it's undefined here at -2, and it's undefined here at -2. Meaning for neither of these functions is it defined at -2. In graphing, we often indicate this with an open circle, which is why up here you see how there's that little open circle. There's a little open circle down here. That open circle indicates we do not get that value. And so if we want to actually write things like the domain and range, our function, let's do that. So let's talk about domain. Using the graph, I know that everything less than -2 works. So from -infinity to -2 works. And everything to the right of -2 works, because the second one, from -2 to infinity. But you'll notice that -2 does not work. If I try to plug in -2, I can't plug in the top one because I not have an equal sign, and I can't plug in the bottom one. And so this ends up being the domain for this piecewise function. On the previous one, the domain for this function would be all real numbers. So from -infinity to infinity. Because everything less than 3 works, everything bigger than or equal to 3 works, including 3. So that means that every number works. There's no gaps. There is a breakdown in the graph, right? There was some separation in the graph, but every x had a value. And you can see that right here. Every number that is less than 3 has a value. Every number that is bigger than or equal to 3 has a value. If both those things are true, then all numbers have a value. Whereas in this one, that's not the case. -2 does not have a value, so you have to exclude it from the domain. What about the range? Well, let's go back to that graph. So, what's the lowest value we have in this graph? Well, if you look at this graph and you zoom out some, you'll see that the red line and the blue line both go down forever. Which means that for this function, -infinity is the lowest possible value we have. But what's the highest? Now, for the blue line, the highest is different than for the red line. Now, the question is, are there any gaps? So remember, we're going up the axis. So at -30, there's the spot where we touch the graph. At -25, there's the spot where we touch the graph. -20, there's the spot where we touch the graph. -15, there's the spot where we touch the graph. -10, there's the spot where we touch the graph. -5, we don't touch it here, but we do touch it over here. And so that's fine. -4, -3, -2, -1, 0, 1, 2. The problem is, what happens when we get up here towards +3? As we get really close to +3, notice we get near +3 on the y-axis, but not quite there. See, it's at 2.97 on the y. And if we zoom in a little bit more, we can get even closer. 2.98. Okay, we get closer. 2.99. That's really close to 3, but we don't ever actually get to 3, because when we get to 3, it's undefined. And so for the range in this function, the top value is a 3, and we do not get to it. Meaning that's how we write our domain for this, or our range for this function. It looks like there's another gap here. If we go back to that picture one more time. It looks like there's another gap right here. Like there's a gap. Remember, the question isn't if it touches it on the red line or if it touches on the blue line, if it touches on either one. So here, like at -4, it's still touching the graph, just on the other side, on the other piece of it. As long as it's touching it somewhere, it counts. So here at -4, we do have an answer. Here at -2, we do have an answer. Here at 0, we do have an answer. Here at 2, we do have an answer. But at 3, we do not have an answer. We get close, but it's not quite there. And so we see the domain and range as follows. The domain is everything except -2, because every x has a possible y. The range is from -infinity to 3, because that's a place where we will cross the graph everywhere except at everything bigger than 3. So, let's look at another. Before we do that, let's talk about that second piece, which is evaluating. If I asked you about f of -1, f of -2, and f of -3. Well, this first one, f of -1 would have to be plugged into the bottom equation. -1 is bigger than -2, so I got to plug in the bottom equation. So we do -1 plus 1. Double negative would make that positive, plus 1 would make that 2. So f of -1 would be 2. Notice we only use the bottom equation because -1 is greater than -2. At -2, notice I can't plug in the top equation and I cannot plug into the bottom equation, meaning the solution for -2 is actually an undefined solution, which is good. That's also how we know that the domain is broken. Because there is a time when I plug in a number and do not get an answer. At -3, I'd have to plug into the top one, which means I'd have to do 2 times -3 minus 1. That'd be -6 minus 1, which would be -7, of course. And so that's how we approach these piecewise functions. Let's look at one more. f of x is equal to, let's see, x squared minus x cubed. That sounds fun. And the square root of x squared plus 1. And for these two, let's have this one start at x is less than 3. And for this one, x is greater than 4. Okay. And let's ask some questions, shall we? You know what? Less than or equal to 3. All right. Let's ask a couple questions. So we're going to answer questions about the domain. We're going to answer questions about the range. We're also going to answer questions about these three. F of 0, F of 3, F of 4, F of 5. Oh, I apologize, I'm off the page. My bad. Sorry. Okay, let's answer these questions. So I'm going to start by doing these ones. These are the easier ones to do, because all they require me to do is to look at this function and plug it into the right part. So let's do that. F of 0. Well, is 0 less than or equal to 3? Yes, so I need to plug it into the top one. So I plug in 0, 0 squared minus 0 cubed. That'd be 0 minus 0, which is of course 0. Plugging in 3. Is 3 less than or equal to 3? Yes, so should I plug it in the top one? 3 squared minus 3 cubed. 3 squared would be 9. 3 cubed is 27, which would be negative 18. That's acceptable. What about 4? Well, 4 is not less than or equal to 3, so I can't plug it in the top one. I also cannot plug it into the bottom one, which means that this one is no solution. And then 5 would fit in the top one, because 5 is in fact greater than or greater than 4. If I plug in 5, this would be the square root of 5 squared plus 1. 5 squared is 25, plus 1 would be 26. And so there are my 4 solutions. The harder question is always about the domain. So just like before, I'm going to go to Desmos to help me out here. I'm going to type in these two functions. Let's see. I'm going to cheat here. Once you've done one, you can kind of cheat a little bit. Okay. This first one starts at 3. There's no symbol for greater than or equal to, so if you go to the greater than symbol or less than symbol and then just hit the equal sign, it will add in that symbol. So there's that. And then I type in x squared minus x cubed. Now this is everything greater than 4, and this one is the square root. So go over here, oops, square root of x squared plus 1, boom. Okay, well, let's take a look. Well, let's talk domain. So I can see if I keep going to the left, I'm going to keep getting answers. It's going to get really big, but like I will get an answer up there. And same if I keep going to the right. But let's investigate what's happening here in the middle. If you look here in the middle, you can see that there is a breakdown between these two. This one stops at 4, this one stops at 3. Now, the 3 is included. The 4 is not included. So, when I write down my domain and range, let's talk about domain. When I write my domain, everything to the left of 3 works, including 3. Everything to the right of 4 works, but it does not include 4. So this function, that would be the domain and range. Notice that it's just an interpretation of these two pieces. Now, the harder one for many of these is always going to be the range. So let's look back at this. So if you look at our function, you can see that as we keep going up, like we keep having values, right? It seems like as if no matter how far up I go, I will always have a point in the graph. So if I go up to 10, there's a point right here, and another point over there. As long as it's somewhere, it's fine. 15, there's one here. 20, there's one there. So if I keep going up, I seem to appear to keep touching the graph somewhere. Now, is it farther to the right? Yes. Is it farther to the left? Yes. But I keep getting points. Down here, like the blue line stops right here, but notice the red line has got it covered. So the blue line kind of stops right here at what looks to be pretty close to positive 4. Like that's really close. But if you notice that it's right there is got an answer. And then it keeps going down, 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 down. But eventually notice it does stop. It stops at negative 18. Which means that on the y values, negative 18 is the lowest acceptable y value. Remember when we type in the domain and range? When we write it out? For the domain, you include all the possible x values, starting lowest possible accepted to the highest, and then any breaks in between. The lowest x value is negative 18. It's the lowest point on the graph where I do have a y value. The highest, it goes on forever, so that means it goes to infinity. So there's our domain and range for this function. You are tasked tonight with looking at a piecewise function and determining these two components. Determining, exact values, to be able to plug into a piecewise function, as well as being able to use a domain and range. Use the graphing calculator to help you. Before I go, I want to showcase how to do these graphs using a TI-84. If you have them, it's really helpful. If you don't, you can still find the piecewise using Desmos. Let's take this function right here, and we're going to plug it now into a graphing calculator using a TI-84. Or if you're using things like WabbitEmu, which is a popular one that I use, it's a graphing calculator. You do it the exact same way. There we go. Alright, so let me put my graphing calculator here. Right there. Boop. Okay. So how do we get this thing to graph a piecewise function? Now, to graph the piecewise, it is a little bit more work than the other one. That's why it's so common to use Desmos for a lot of this stuff to help you, because it really is helpful. But for now, let's go ahead and take a look. I'm going to start by making sure everything's in standard. There we go. Yay. Alright. To plot the first one, the first thing we're going to do is we need to type in parentheses the entire first equation. So, in parentheses I type in, first equation is x squared minus x cubed. We close parentheses. No matter what that equation is, we put the entire thing in parentheses. We then divide it by, and on bottom, also in parentheses, we put the domain, which is x is less than or equal to. Now, there's no less than or equal to symbol on this, but there is one under what's called the test tab. Right here you can see the little test button. We had second math, and that's test, and that's where you'll see this list of possible things. So I go down here, I went to less than or equal to. It's right there. Oop, I hit too many times. And so I put less than or equal to, and I put 3, and then close the parentheses. And what this will do is this will grab this function, but it'll stop it at positive 3. I then have to do the second function on a second line. So again, I put everything in parentheses, so parentheses. I would then put the square root of x squared plus 1, close that parentheses, divided by new parentheses, and then I type in the second equation, which is x is greater than 4. And so this allows me to type in both functions. Now, the cool thing about this is just like you can see down here in these little previews, this graph will stop at 3, and I'll zoom out so you can see that it does in fact stop at 3, and then it picks up over here at positive 4. I can go to my zoom, I can zoom out a little bit, boom. We can see that it will follow the same path. It will just stop over here at 3, there it is, and then it picks up over here at 4. The cooler thing is the table feature, which you see over here on the right hand side. Notice how for negative 5 there's a value, for negative 4 there's a value, negative 3 is a value, negative 2, negative 1, 0, 1, 2, 3. 3 has a value, meaning 3 is in the domain. 4 does not have a value, meaning 4 cannot be in my domain. And you can switch this up and use this to find any values using the calc command, which is pretty neat. And so this is how you would type it in using TI-84 instead. And so no matter what calculator you're in, it should be able to do piecewise. If you have a different kind of calculator and you're not quite sure how to do a piecewise function on that calculator, I have good news. Google it. Type in piecewise function on and then name your calculator. And we'll pull it up for you. And we'll walk you through it step by step. I guarantee there's a YouTube tutorial on it somewhere. Okay? That'll be it for today. You only have 4 problems tonight. It's a pretty short assignment, but these are all piecewise. And so it's all new material for some of you. Use that to your advantage. Figure out how to do both domain and range and plug in those values. And I'll be on my Zoom call at noon if you guys need anything. Otherwise, I'll see you guys on Monday. Have a good weekend.